This is the second video in a series about an early microcomputer operating system called FDOS. It was introduced in early 1975 by a company called ICOM to support this disk drive subsystem that you see here, the FD360. They had introduced that back in 1974. And from what I can tell, FDOS is the first commercially distributed disk operating system for a microcomputer. And in the first video, I go through the reasons why I come to that conclusion. I describe some of the history, the timeline of the early computers, disk drives, and operating systems that were popping up in the mid-70s. And then in the end of that video, I did a quick demonstration of what it was like to boot up and take a look at some of FDOS's commands. Now, if you haven't watched that video yet, I would really recommend watching that first. It'll give you a background you need for this video. And to help you find it, I put links to it in the description of this video. If you were using FDOS in early 1975, you would have been running it on the computer that you see here. This is an Intellect 8 Mod 80 made by Intel. This is the first computer to use an 8080 processor as its CPU. Now, Intel sold this as a development system to companies that were embedding an 8080 into a product that they were developing. And so as a development system, it could serve as an in-circuit emulator and debugger, and it could also serve as a standalone software development station for writing 8080 assembly code. However, as a software development station, it assumed a teletype as a console and the paper tape reader and punch on that as mass storage. The editor and assembler they provided loaded and executed from paper tape. And your files, your source files, object files were all done on paper tape. And as you've seen in other videos I've made, that's just a miserably slow and difficult way to develop software. So ICOM and their FD360 and FDOS came along and gave you a way to speed that up by a factor of well over 100, just dramatically faster and quieter and easier to use. FDOS provided an editor and assembler that were just completely compatible with the one that Intel would provide. So it was just a very quick switch over, no real learning curve. And ICOM made this basically plug and play with a board that went into this Intellect 8. And then FDOS just booted right up using an EEPROM that was on there, and you were up and going. And again, the syntax of the editor and assembler was what you might have already been used to using the Mod 8. So let's go ahead and do a deep dive in this video into FDOS, see what it was like for the typical engineer and developer who would have been using it to use it for creating and running software. All right, we're going to be running FDOS on this Altair 8800 computer today instead of on an Intellect 8 because unfortunately I don't have an Intellect 8 computer. However, as far as FDOS is concerned and the disk drive and the interface board that plugs into the computer from the disk drive, it's virtually identical. So everything in this demo will still be very pertinent to what you would have seen on Intellect 8 back in early 75. All right, to boot FDOS, all you have to do is jump to the EEPROM that's on the interface board that was supplied by ICOM along with your disk drive and with FDOS. So in the Altair, that's up at C1000. Examine that and hit run. See the disk drive activity, you see the lights as it's booting FDOS. Let's go over here to the screen. And there you can see our startup prompt. The exclamation point is the command prompt from FDOS. We're running FDOS 3, as you can see here, so that's obviously not the same version that was running in March of 75. However, there's very little difference between these FDOS versions, and so most of this will be exactly the same. Anything that's different, I'll be sure I'll go ahead and point it out. All right, first thing we're going to do is take a look, see what we have on this disk, and you can see we have the editor and the assembler and a variety of other things. If you were a user of FDOS in early 75, you would have been developing 8080 assembly language software. So probably the best way to really show what this is like to use is to go ahead and let's just work on some 8080 software. So as we've done our directory here, we can see the editor and the assembler down here. And the program I'm working on has to be one of these. I'm thinking it's this demo 1 program. So what you might do is run the view command to look at demo 1 and see what it is. And I can page through this one page at a time by hitting N between pages. I can hit P to back up a page, B go back to the beginning of the file, or just hit return and I'm done. But anyway, yes, that is the file I was working on, so now I want to edit it. So you just type edit demo 1. Now you have to follow the file you're editing with a file that you want the editor to create when it's done. It's always going to write a new file. Even if you didn't change anything, it's going to write this new file that is the result of your edit session. Remember, we can't edit things in this. Well, you can't rewrite the same file, so it's going to do a whole new file here. Now, what I've done is use this nomenclature of a digit after each file name to keep track of my versions, let's call them. And what that ends up doing is leaving me with just 4 characters for file names instead of the 5, which is already pretty tough. So when it comes to source files or anything like that, you're down to just 4 characters that can uniquely identify the file. And to me, that's a pretty strict limitation. And again, this is the one thing I'm not really thrilled about FDOS. Everything else, I'm pretty impressed, especially for the time frame in which it came out. All right, this editor is a very standard line editor, just like you ran into a lot in the early days. And this particular editor duplicates all the commands and user interface of the actual editor that would have come on paper tape with the Intellect 8 from Intel. So there's basically no learning curve for an engineer that might have switched over to FDOS midstream. All right, like most of these early line editors, they don't bring the buffer or bring the whole input file in because there's probably not enough RAM. And so you append just sections of it at a time. A brings in 50 lines. So if I were to type, say, 99 lines of this file, what you'll find is that it just stops there after 50 lines. Now you hit append again, you can bring in another 50 lines. However, what I want to do is up at the beginning of this file, so let's just type that again, whoops. See, 20T. All I really want to do is make this file run at 200 instead of 400. You can see right here it's loading at 100, and I need that to load at hex 200. Let's pretend this is a program that's running on the target machine that as an engineer I'm developing. So I'll change 0100 hex to 0200 hex. Okay, and now you can see we've got that 200 hex like we want. Now to edit this, when you exit this now, it will write out these changes and then copy the rest of the file that we haven't touched into the new file with this part that we have changed, and then we'll have a complete file. Now what I want you to do is watch this computer as I do the exit. All right, so I'm going to type exit over here, and you'll see we have some slow light flashing. That is it writing the file. This rapid light flashing is now reloading FDOS. So what happened is the editor was a large program. It actually just overwrote FDOS and clobbered it completely. And then when it exited, it had to reload FDOS. And of course, as you might guess, the assembler is a large program. It has to work that way as well. And in fact, because you didn't have a lot of memory, most programs overlay this command processor of FDOS, wiping it out, and they exit by reloading FDOS. You see some of that same thing with warm boot after programs run in CPM. All right, so we're now back from the editor. We do a directory, and we can see now that we have our demo 2, which is our second source file. And we can do a view just to make sure it looks right. And yeah, sure enough, we're at 200 hex instead of 100 hex, so that looks good. So now we assemble it. Assemble, give it the source file name, and then you give it the name of a program, of a file you want to write with the output of the assembler. This will be an Intel hex file. We'll call it just demo. And then you have to follow it with a parameter that says what you want in terms of listing, symbol, table, and output format. The 3 tells the assembler that we want a listing coming to the screen and that we want an Intel hex file written. All right, it's still loading the assembler right now. I should have shown you the lights, I guess. Okay, now it's actually doing the assembly, and now here we see the listing coming out. And as it's giving us this listing, that's technically going to the list device, which could be a printer. I have it coming to the screen for now. It's written all those files. Right now it is reloading FDOS. And now FDOS is back and running. So now if we take a look, you can see that we've got our demo file now. And if you take a look at that, we can see what it is. That's a very short Intel hex dump of what was produced by the assembler. All right, so now we want to run this file. How would you run it? Like a lot of Intel assemblers, 8080 assemblers, it generated Intel hex. But is that what format do you actually have to run on this machine. So for example, in CP/M, you would now run the load command to convert Intel hex into a COM file, which is pure binary. But what does this system require? Well, interestingly, the actual executable format of all programs in FDOS is Intel hex. For example, if I look at the assembler, it's an Intel hex. If I actually look at the operating system itself, it's an Intel hex. All right, so this program is already in a format required to run it because Intel hex is the native executable format on FDOS. Now, this might seem kind of odd, but there are some advantages to that. Number one, Intel hex allows very disjoint memory space within a single file. It doesn't have to be contiguous like in CP/M. That can come in handy, and we'll see that later in this video. Also, it allows for much simpler transfer of files by keeping everything in the printable range of ASCII. For example, there's a good chance you're going to need to punch this to a paper tape to bring into another device or into a programmer that maybe you're not using the one on the front of your Intellect 8 or something. And teletypes just did not like anything other than printable characters. If you ever tried punching a binary tape on a teletype, you know, it'll eject paper and it'll ring the bell and it'll get stuck on the right margin and hammer a hole in the paper, all that kind of good stuff. So having it all in the ASCII printable range is very handy, especially if you're using a teletype for punching tapes, and exchanging files in general is just a bit neater. Again, also you have a second layer of error checking here because every Intel hex record has a checksum on it. Disadvantage, of course, is the size. It's going to be 2 to 3 times larger than if it was just straight binary, which takes up disk space and also is, you know, half the speed of loading because you got to load twice as much data. So those would be the downsides of it. But obviously they chose to go with Intel hex. Probably the downsides were brushed off a bit because on a disk the size of this, in these early days, it was almost like, oh, we'll never fill that up, even just one floppy. So that's no big deal space-wise. Speed-wise, this is already literally 100 times faster than teletype and paper tape. So getting it 200 times faster, well, who cares? It's just so ridiculously better that it's worth these advantages. So maybe that's some of the reasoning as to why they decided to stick with Intel hex. All right, so enough of that detour. How would I actually run this file that we just created? So to run a program you created, you type run and then the name of the program, which is demo. What this does is load it into memory and then drop into the monitor, the ROM monitor of the system. Now on the Intellect 8, that would have been a very sophisticated monitor that was used for in-circuit emulation, debug, single step, dump registers, breakpoints, all that good stuff. So it really would make sense, for example, if demo was a program you were loading into your target unit to try to test it while using your Intellect 8 excuse me, as your debugging device, you would have run it this way. Now on an Altair there is no standard monitor, so in the interface board is a very trivial monitor called the mini monitor. That's inventive, and that's the greater than sign is the prompt we're seeing from that, and this monitor just gave it a place to go when it was on the Altair. We can jump to any address just by typing it in and hitting return. So now this is running that program you were just looking at. Asking for a message, how many times do you want to display it, and there you go. All right, simple as that. Now, if this was a program you'd load it into your target machine, at this point you would probably, want to go back into FDOS. So to do that, you would go over to your console and just do a hard boot. So I'm examining C1000 and hitting run after I stop the machine. And then I'll be back up in FDOS, ready to do something else. Okay, so we're back in FDOS, having just, let's call it debug demo over on our target hardware using the Intellect 8 as our in-circuit emulator. But what if you actually wanted to write a program that ran on the Intellect 8 or on your computer? Maybe a game, of course, or some utility you've written. How would you just make it run rather than having to go into the monitor and type the address or even know the address? Well, there's a provision for that by editing the stop record, the end record, in the hex file. So if I edit demo, which is the hex file, let's make a new one, call it demo J for jump. We can actually edit the end record and put in a starting address in there. So we'll bring the file in, Take a look at it. All right, so on this end record, that's all zeros. The first byte, which is the first 2 digits after the colon on this last one, length is the length of the record. If it's 0, that means this is the last record. The next 4 bytes, 2 bytes, which is 4 digits, is the address. You can see these all have an address where we have data. If that is 0, which is the default for an end record, then it just jumps into the monitor like we saw. However, if it's a value other than 0, then it is the address that it should auto jump to. So let's change 0 length and then 0000, which is the 0 start address, which means just go to the monitor. Change that to, got to keep the 0 length, but now we want to jump to 200 hex. Interestingly, it uses big endian, even though it's Intel and Intel hex records. All right, so now we can exit. And then we'll take a look at this just to make sure it looks right. I guess I should have done that before I exited the editor. All right, so this jump version, if we look, we have our 00 length, meaning end record, and now it's 200 instead of zeros in there. So now if we run this, run demo J, whoops, and let's see, I can force it to reprint that. Okay, so that's what I actually typed after the deletes. It echoes deletes out. So that's why you see double characters. Okay, so we're going to run demo J. Now, instead of dropping to the monitor, it actually executes it for us. And if I hit return, I have this set just to go back into FDOS. All right, so that's how you'd write a program or modify a program so that it automatically ran on this machine when you hit run. Now, you would think you could do that in the assembler. Most assemblers, you can put like a starting symbol as an argument for the end directive. And possibly the version back in the beginning in 1975 did do that, but the assembler that's on this newer version doesn't have that feature. And one reason it might have changed is because in this newer version, you can actually run a program yet another way, and I'm going to show you that in a minute. But let's continue here like it would have been in 75. At this point, we've got quite a few things on the disk. Maybe you want to clean up a bit. So we could delete some files. Let's say we want to delete, and you can actually list files here. We're not going to use the demo that doesn't jump on its own. I don't need demo 1 anymore. Anything else I can delete? Not really. All right, so let's delete those. But you could list 4, 5, 6 items, and it deletes them all for you. And now you'll see that it's got an attribute of 99 for demo 1 and demo. So they're deleted. If you try to look at them, it's going to say they're not there. Oops, that one really isn't there, is it? But they're still there. You can always recover them just by doing a change attribute on demo, let's say, changing it back to 0. See, now it's 0 like all the others. So you got demo now has 0. And now it's back and you can actually see it. All right, but let's go ahead and delete it anyway. Delete demo. And now we can run the pack program. What this does is anything that is deleted, it actually will now overwrite it, move all the files up to the beginning so that all our free space is contiguous at the end. And again, we had lots of space free on this disk, 1,100 sectors free, so we certainly didn't need to do this yet to free up space, but that's how you clean up something like that. All right, now I have another disk in here too. This is the second drive. You do that by, you say list and then a device number. Boy, I switch those 2 letters every time, don't I? So that's the second drive. List or list comma 0 is looking at the boot drive. Let's say you wanted to copy a file. How did you copy a single file? I want to copy the demo jump program over to that second disk. Well, there was no file copy routine in this, probably because I guess they just expected you to use the editor. So you could type in demo J, and then for the output file, you want demo J over on drive 1. So that :1 is how you do a different drive, :2, :3 for up to 4 drives. So what this is going to do is start the editor, and the output file it writes is going to be on the other drive. So I can just immediately exit. Even though I made no changes, it still copies the whole input file to the output file, and it'll be identical since I've made no changes. So now, God, I did that so much. So now you're looking at another disk. We have demo J on the second drive. And you can run something from the second drive oh, missed it, just by specifying that drive indicator after the file name. All right. To be truthful, that's about it in terms of, doing development and things. One thing you might do is run this copy program. Copy lets you back up an entire disk. That's all it does. It just copy drive 0 to drive 1. Some of these other programs weren't on the original, but copy would have been back there in 1975 as well. And it was really intended to be a replacement for the paper tape assembler and editor environment, and just give it to you here on disk, where it was much faster and easier to run, and you had files that were easily backed up by copying it to another disk, so you had backups of your files, much easier than messing with paper tape. Now, obviously running the assembler and the editor, which are both just files, just like our demo programs, those took arguments. I didn't have to type run. That was kind of a nice feature. What if I wanted to write a file copy program or some other program that worked a lot like the editor or assembler, where I had an input file, an output file, or maybe just an input file? How would you make one of those? Well, the original FDOS didn't have that, but they added it very quickly. By September of '75, they were advertising FDOS 2. And FDOS 2, one of the main things it added was the ability to run any file, like our demo program, but provided parameters for an input and output file like you've done here with the assembler and editor, where FDOS set that all up for the programmer, set it all up for the program. It makes it really easy to use, and that's what we're going to look at next. As I mentioned in the previous video, FDOS is comprised of two main portions: a resident portion that doesn't go away, and a non-resident portion that can be overlaid and eliminated from RAM. That's the command processor that we've been running, is the non-resident portion. The resident portion is an EEPROM on that interface board that we jump to in order to boot FDOS. So along with the boot code in that EEPROM are routines to read and write FDOS disk files, as long as they've been opened already. Also on that board is a small amount of RAM, 128 byte little scratch pad RAM. That has enough room for some parameters, and it also has room for two file control box that allows two files to be opened at the same time, one for input, one for output. And let's take a look and see how that is all set up and used by FDOS when it runs like the assembler or the editor. If you run the assembler, you would type assemble, source file name, an object file name, and then a parameter that controls the listing in the output files. So when FDOS sees this, it sees that you want to run the assembler, so it says, okay, I'm going to go set this up for the assembler. And the exact same thing is going to happen for the editor, by the way. So the first parameter it finds is an input file. So FDOS goes out, makes sure that file exists, and it opens it. If it doesn't exist, it throws an error, doesn't even start the assembler or the editor. When it opens the file, what it really does is create a data structure or a file control block in the static RAM on the EEPROM board, the interface board, so that it's going to be there even when FDOS goes away. And that includes the information that the disk I/O routines in the EEPROM need in order to read the next byte, the next sector, the next track, etc. Then it looks for the next parameter, which is the output file. It looks in its directories and makes sure that that file does not exist. It can only be a new file. If it's an existing file, again, it'll throw an error without even starting up the assembler at all. If it is there, then it opens it up, creates another data structure, another file control block for an output file in that 128 byte RAM on the interface board. And as part of that, it tells the routines, here's the drive to use, here's the track it starts on, here's the sector it starts on, and how big it is. Now when it comes to the output file, the size of this file that it tells the file control block is basically the rest of the disk, all the free space on the disk. In other words, in this case, it would say it's 1122 sectors big. That way, the assembler or whatever routine gets called can sit there and write till it runs out of space, or of course the file is done, which would be more typical. And then I'll tell you how that ends up getting closed and the proper size is assigned in the end. All right, and then finally it looks for a third parameter, and that's got to be a number. And FDOS converts that into a single byte and then puts that in a specific spot in that same 128 byte RAM. So at this point, the files are open. Everything needed for file I/O and for the program to look at is in the 128-byte RAM on the interface board with the EEPROM. FDOS itself can now disappear once it gets the assembler editor loaded. All right, so how does FDOS load the assembler on top of itself while it's getting clobbered? Well, it does that by calling a single routine in the EEPROM. And that routine will load an Intel hex file into RAM and then jump to it. So FDOS can disappear at the point it calls that routine because the actual loading is being done by a little bit of code in the EEPROM. All right, so we're talking about jumping to the start of the program just loaded, the assembler or the editor. How does it know where to jump? Well, that is a vector in the same 128-byte RAM out on that board. So FDOS theoretically could put something in there before it disappeared, or the actual program loading, since we're loading Intel hex records, could have a hex record that basically said, here, start me at this address. So let me show you that. I just aborted that command. So if I, let's see, if I do a view of assemble, you'll notice here in this very first record, this is 3 bytes long. It's getting loaded at BC18. That is the jump vector. And it's loading a jump to where it really starts, which is 2100. All right, so that's, like I mentioned before, one of the advantages of using Intel hex as your, quote, binary format is that you can have completely disjoint space because we're going to load at 2100 and yet we just updated RAM up at BC18 to put a jump vector in there. Now, if you put the jump vector into the end record like we just did in the previous demo, that takes precedence over this BC18 vector. But most all programs that use the same format as the assembler and editor are going to use the BC18 vector to be consistent. All right, so the editor and the assembler have this nice mechanism where FDOS sets up everything for them. It opens the input file, opens the output file, passes it a parameter. When those programs start, they don't have to do anything but start reading and start writing. And they don't even have to figure out how to close the output file and update directory and put the right size in it. All they have to do is exit to FDOS by calling an EEPROM routine to reload FDOS that then jumps to an update entry point in FDOS. That update entry point then goes and looks at the file control block for the output file, automatically updates the directory with the new file name, gets the right sizes in there and everything. So it makes the program very simple. And this is kind of handy. If you've ever done this kind of work in North Star DOS or, well, even CP/M, it's simpler there, but North Star DOS and Polymorphic's System 88 and some of these others that have a similar operating system here to FDOS, there is more code to do all the file work we just talked about than there is to actually, for example, just read and write a file if you're writing a copy routine. So this saves a huge amount of work. And even though it's a rigid structure of input-output parameter, that'll fit probably 90% of the programs you're going to write. So the folks at ICOM saw the power of their assembler and editor call routine. And like I mentioned, in September of '75, so not too long after they came out with FDOS, they added the ability for any program to get started the way that they started the assembler and the editor. And what they did is they added a new command in addition to run. So instead of run, they added a command called run go. So if you typed run go, let me try that again, run go, then you could type any program name. For example, I have a program called fcopy for file copy. So file copy, you give it a source file, for example, demo, and then a destination file, say demo4. This would start fcopy after it opened demo for it, after it opened demo4 for output. You can put a parameter here if you want it. I have another program that does use a parameter. Then it would load fcopy and jump to it. All fcopy has to do is start reading and start writing, and then just exit to the update entry point of FDOS, which would reboot FDOS, update the output file, and it's done. Now, that run go ended up being kind of redundant. They realized you really didn't have to type that. Let's do it like, not that they looked at CP/M to do it, maybe they did, who knows. They just did it and said, hey, if we don't have that file, whatever you type, for example, I typed Mike, that doesn't exist. However, what it did is it went and looked for a file called Mike to see if it was going to do an implied run go of Mike. That's what they called it when they created FDOS 3. So FDOS 3 was a bit later than FDOS 2, but in FDOS 3, which is running what we're running here, they get rid of the run go part, and now it's just an implied run go. So in the end, here's what happens. You can write any program you want. I wrote fcopy, and you can say source file, and then a demo, a destination file. And I did something wrong. Let me see what files. I don't think I have demo 1 on here. So oh, by the way, fcopy did not generate this error. FDOS looked for demo 1, couldn't find it, and it spit out that error. All right, so let's copy. I think it was demo 2 I had, right? And let's just call it demo 4. All right, so fcopy was past demo 2, already opened. It was past demo 4's file information, already opened. So fcopy just goes into a small loop, copying one to the other, and then exits to FDOS. And now if we take a look, you'll see that we have demo 4 here. And it's going to be, of course, the same thing as demo 2 was. Let me show you that source file. So we'll edit demo 2. I'm going to show you what happens if you don't specify an output file. This is not going to complain. Edit doesn't require it. But it's going to try to write something, and since it has no information, it's going to just write garbage to the disk, which we don't want, of course. And so if you ever do this, or if you ever want to exit the editor without writing anything, you'll basically just stop the machine and cold boot FDOS yourself manually. And I'll show you that in just a second. All right, so let me bring in the file copy routine I wrote. Actually, no, that's not what I wanted to do at all. Well, so let me go ahead and do the reboot I talked about. So I'm going to stop the machine, examine C1000, which is the boot ROM, and hit run. So this is one way to get out of the editor without letting it write anything. All right, so the file I want to do is fcopy1. That's the source file. All right, so I'm going to go ahead and bring that up in the editor so we can look at it. And I'm going to go ahead and give it a output file name just to be safe. And I'll show you how simple routine can be with FDOS doing all the setup for file I/O. I'm going to do a few appends so this whole thing is in there. Let's see if I got everything now. Nope, not quite. All right, so that's got the whole program in there now. All right, so let's take a look at this. So here's basically the program starts up, checks to see if you provided any parameters at all. If not, it puts up how to use it. And then it just jumps here to read buff. So this is the whole program. We get a stack pointer. This is how many bytes of data. I've allocated a buffer of about 4K to read at a time, and a pointer. And then it gets into this loop where it reads a byte, moves it into memory. If it's end of file, it jumps to end of file. Otherwise, it increments the pointer, decrements the number of bytes left, and goes in the loop. So it just stays in this loop until it's either done the whole file or the buffer is full, at which point then it jumps to go write that buffer. So let's go ahead and take a look at that. That went too far. And so in writing, I just do the opposite, where I get the buffer, pull it from memory, write it, increment the pointers and the byte counter, and loop. And at the end of that, if we've hit EOF, then we're all done, and we jump to the update vector that I talked about, which reboots FDOS and goes to the update entry point in FDOS, which closes the output file. So this is the whole routine. Now, by the way, you probably noticed here that file I/O is byte oriented. It's a byte stream. You just read a byte at a time, write a byte at a time. You don't know anything about sectors. You don't know anything about tracks. So, very simple way to organize this. But that's really the whole program. It doesn't have to do any opening, closing, verifying, much of anything in order to run. All right, so this is going to write fcopy 2, but I don't really even need it. Now, we're going to talk about this speed probably in the next video, where we can speed this up as a result of what they learned when they made the 5¼ inch micro floppy version, which these big hex files began to make a difference, and the fact that 5 1/4 is half the speed of an 8-inch also began to make a difference. I wrote another program called PCGet. I have a PCPut that I'm working on that gets a file using Xmodem from a PC. Obviously, this is a modern version. So PCGet gets a file. So what would I put for input file? Well, you put nothing. Output file is whatever I'm getting. Let's say I was getting a file called test. And then a parameter, I can tell it to use the console port or some other port on my serial interface port. If I put nothing, it just gets it from the console port. Now, I'm not connected to my computer to retrieve it, but that shows you how you would use this. If you're doing a PC put, that's taking a file on your disk, sending it out to the PC, then the source file would be in the input file position. So here you can see I moved to the output file position by having a blank spot for the input file, and here the input file would be the parameter, and you don't have to bother listening to the ones afterwards. Now, if you wanted to do a different port, you'd have to do this to get out to option 3. So this will write through port 1 instead of port 0. So pretty much like you'd expect. So the structure it requires, where you do command name, input file, output file, parameter, maybe that's a little restrictive, but again, it's not bad, and boy does it make the program simple the way this sets it up for you. All right, that's probably going to be about all I could squeeze into this video. I think what I'll do is do one more video where I show this running with their micro floppy controller on a 5 1/4-inch disk drive, quite a different hardware setup, and in that we'll look at how they ended up, it's still Intel hex records, but then combined with a binary loader as part of that, where it's compatible either way, Intel hex, ASCII, or binary. And that gets the files a lot smaller so that it'll fit on a 5 1/4-inch disk. And therefore, since they're smaller, they're much faster, which was needed for the 5 1/4 because it runs at half the speed of an 8-inch. All right, well, that does it for this video, and look for that next video on the microfloppy to come soon.